Assalamualaikum and hi to my students. This video lecture is about indirect method. The title is wrong at the second slide. Yeah, I know. Just change it to indirect. We have modus ponens. We have also modus tollens. Modus tollens, the argument starts with not Q implies not P. The second argument is not Q. Therefore, you show as a conclusion not P. Indirect method is also known as a contrapositive method because it is based on modus tollens, method of denying. This method also is logically valid because you know that P implies Q is logically equivalent with not Q implies not P. They are logically equivalent. Therefore, modus tollens is also a valid argument that can be used. However, it has some perks anyway. There are better ways. Sometimes direct method is much more easy, hence the name direct. Indirect method can apply to some cases. My advice to you is that always try to prove by using direct method first. If it fails, then we use the alternative method of indirect method. If it also fails, then you use the least popular proving method, which is a contradiction method. Why some statement cannot use direct method? This is one good example. I start first with why direct method sometimes fail. Okay, this statement, I need to prove if x squared is odd, then x is odd. If I use direct method thinking, I always start with this. Let x squared is odd. So I try to make x squared equals to 2k plus 1. K is an integer. Start the definition first. What is x? Based on some calculation of algebra, then x equals to plus minus square root of 2k plus 1. There you have it. X equals to the square root of 2k plus 1. What is that? Definitely, square root 2k plus 1 is not necessarily must be odd. It does not show the shape of 2l plus 1. It's a square root. I cannot guarantee that this thing is odd or not. I cannot conclusively say that if x squared is odd, then x will be odd. This is not the representation of odd. If odd, it should be in this manner, right? L plus 1 pun boleh, 2m boleh. The alphabet is not the concern. The representation of how you show is odd or not. This is definitely not necessarily odd. This is where the case where the direct method fails. We need another approach to do this. By using indirect method, assuming this is a normal, P implies Q. You state that x squared is odd is a statement. P x is odd is Q. You should convert it into a contrapositive form. Not Q implies not P first. Although the original statement says if x squared is odd, then x is odd, because we are using indirect method, we should first try to change the structure of this statement. For example, if I change this, if x squared is odd, then x is odd, what will be not Q implies not P? It will change, become if x is even, If it should be not odd, but right now we have only two universe in the case of even and odd, even and odd. Therefore, not odd guaranteed to be even. I need to show that if x is even, x squared is even. And you can use the direct method thinking back. How to prove if x is even? I let x equals to 2k, then x squared will be 4k squared. Again, 2k squared becomes 2l. L equals to 2k squared, and L is also an integer. And this proof seems familiar because it is the same like the previous video lecture of direct method. Perhaps the more important part right now, some of you at this point might confuse why we need to prove another statement. Again, this is indirect method. Actually, if you manage to prove if x is even, then x squared is even. It is logically equivalent with P implies Q. My conclusion right now is that right now I just prove to you guys is that if x is even, x squared is even. But the original question is this. The original question is the top one. I managed to prove if x is even, then x squared is even. Logically equivalent, I also proven if x squared is odd, then x is odd. Finish. The proof is complete. It's a little bit different from direct method. Instead, we trying to prove if x squared is odd, then x is odd. We prove the contrapositive form first. We prove that x is even, then x squared is even. If we manage to prove that, also we manage to prove that the original statement if x squared is odd, then x is odd. This sums up the proof. We proceed to the next example. Prove that if f5n plus 2 is odd, then n is odd. I always like to start why sometimes the direct method fails first, so that you can be more convinced that we should use indirect method for this case. If I happen to use the direct method, I will not get the answer. Normally, I will use this. I let this 5n plus 2, I believe it to be some odd integers. And based on arithmetic operation, I need to find what is n. And n happens to be like this. 2k plus 1 minus 2 minus 1 over 5. And this is n. And n equals to 2k minus 1 over 5. And this is definitely not look like an odd integer. This one. This is not in the form of odd integer. You cannot be convinced. I cannot convince my audience to show that this n is odd. In this case, direct method fails. It's not that convincing. Suppose I want to use alternative method of indirect. So instead of I'm trying to prove that if 5n plus 2 is odd, then n is odd directly, I want to prove this instead. I want to prove if n is even, then 5n plus 2 is also even. Then we prove it as usual. n equals to 2k, what is 5n plus 2? I might do this slowly. 5n plus 2 equals to 5 times 2k plus 2. Do the algebra. Comes 5k plus 1. Let me check. Yeah, factorize 2 outside. Okay, then as k is an integer, the final product 5n plus 2 can be made as an integer L. This L is 5k plus 1. I managed to prove to you that if n is even, then 5n plus 2 is even. And at the same time, I'm also managed to prove that the original statement or theorem is also true. This concludes the proof. As a conclusion for indirect method, again, try to use direct method first. Sometimes it fails because of the reasons that I told you previously in these two examples. Change into the contrapositive form first. Prove that the contrapositive form is true. Therefore, the original P implies Q is also true. That concludes the lecture for indirect method. If you found it to be if you have some problems, I'll see you again in the actual online lecture. Thank you.